In this video, we'll talk about the zoo of continuous random variables. We'll talk about the continuous uniform, the exponential, the memoryless property, and the gamma random variable. So we'll say that x is uniform AB, where a is less than b are real numbers, if it has this following PDF, which is 1 over b minus a for any real number between a and b, and this notation is very similar to the discrete random variable, but usually we'll specify whether it's continuous or discrete. X is equally likely to take any value in the interval. Here are the mean, variance, and CDF, which you can do the calculations for. Okay, so now we'll talk about the more interesting ones. So recall the Poisson process with parameter lambda greater than 0 has events happening at average rate lambda per unit of time forever. The exponential random variable measures the time until the first occurrence of an event. So it's a continuous random variable with range 0 to infinity, unlike the Poisson random variable, which counts the number of occurrences in a unit of time. So it has range like the non-negative integers. And this exponential random variable is kind of like the geometric random variable because it's like the waiting time until the first event, except here the waiting time can be any real number, whereas for the geometric it had to be an integer. So let y be exponential lambda is the time until the first event. We'll compute its CDF and PDF. And let x of t be Poisson lambda t, which is the number of events in the first t units of time for t greater than 0, because in the unit t, if you have t units of time, then you have lambda t events on average per t units of time. So the probability that y is greater than t means the probability that we wait longer than t time for the first event. So there's no events in the first t units. And this is saying that x of t is equal to 0. And since x of t is Poisson, we can plug in its probability mass function, which is e to the negative rate times rate to the k over k factorial. And you just get e to the negative lambda t. So the CDF is the probability y is less than or equal to t. And this is just 1 minus the probability it's greater than t. So you just get that. And remember, to get the density function, we take the derivative of the CDF. So our PDF is the derivative, and so you can do the algebra yourself, and you get this. So the expected value we can compute, you just do the integral of x times the density dx, and we're not going to do it. Expected value of x squared, again by Lotus, you do integral of x squared times the density, and so you can compute the variance. So we'll say that x is exponential lambda if and only if it has this PDF, and it's the waiting time until the first occurrence of an event in a Poisson process with parameter lambda. And here are the mean, variance, and CDF that we derived. So now we'll talk about the memoryless property. We'll say a random variable is memoryless if for all s and t greater than 0, this statement holds. So what does this mean? Let's let s equal 7 and t equal 2. So it says that the probability x is greater than 9, given that x is greater than 7, is equal to the probability x is greater than 2. Meaning that if we've waited 7 minutes, the probability we wait at least 2 more is the same as the probability we wait at least 2 more from the beginning. So we've kind of forgot that we've already waited 7 minutes. We're just carrying that we wait 2 more minutes. So the only memoryless property, random variables with the memoryless property are the geometric and exponential random variable. So here's a picture. So here's the probability x is greater than 1 for an exponential random variable. So it's the area to the right of 1 of the PDF. Here is the probability x is greater than 2.5, which is here, given that x is greater than 1.5. So only out of this area to the right of 1.5. So if you like hide this curve here, you'll see that the ratio of this area to this area is the same as the probability x is greater than 1. You can kind of see this is kind of a shrinked version of this. And this is why, this is the picture of memorylessness. So now recall, if x is exponential lambda, we derived that the probability you wait more than x seconds, or units of time, is e to the negative lambda x. So if we want to prove the memoryless property, we'll use Bayes' theorem. So we'll reverse the conditioning. And notice that the probability x greater than s, given that x is already greater than s plus t, is just 1. And so we're just left with this over this, and we'll just plug in our formula, s plus t and s, and actually it turns out they cancel out and you get e to the negative lambda t. But e to the negative lambda t is the probability x is greater than t. So this proves the memoryless property. Now we'll talk about the gamma random variable. So we'll say x is gamma with parameter r and lambda if it has the following PDF. Don't worry about this PDF, but we care about what it represents. So x is gamma with parameter r and lambda if it's the sum of r independent exponential lambda random variables. So gamma is to exponential as negative binomial is to geometric. So it's the waiting time until the rth event, not just the first event. And so you can write it as a sum of independent exponential or geometric random variables. And the expected value will be just r times the mean of the exponential, which is 1 over lambda. The variance will be r over lambda squared because the variance of a single exponential is 1 over lambda squared. And so the interpretation is that x is the waiting time until the rth occurrence of an event. And so notice that gamma 1 lambda is the same as exponential lambda because you wait for 1 event.